Also, the neutron flux has been measured fairly crudely with a neutron dosimeter. From Harwell, we calculate that flux to be on the order of 10 to the 4th neutrons per second for a 0.4 by 10 centimeter rod. The thermal data is shown on the next slide. The calorimetric data is presented here. This is the generation of the excess enthalpy. We've done it for a series of configurations, a series of rods, sheets, and cubes. These, we find indeed that the excess heat that is generated by the equations that Professor Yeager talked about earlier are a function of the volume. These experiments were designed to show the reaction as a function, or the heat liberated as a function of volume, so as to distinguish it from any electrochemical reaction that may be taken on the surface. This particular slide shows that the excess rate of heating has been, we have obtained something over 20 watts per cubic centimeter at this time. That has been upped by at least a factor of 3 in the last week or so. The next slide shows the method of measurement. There are many ways, of course, to do the calorimetry. We usually let the cell run for, measure the total heat going in, the total heat coming out. A typical measurement may be after 200 hours, after the cell has been running for 200 or 250 hours. The sloping background that you see, the sloping baseline there, is the increase, the slow increase in temperature of the cell as you are as you're electrolyzing some of the volume, as well as the continued heat of reaction coming out of the center of the electrode. So at a given time, we will inject a certain amount of heat into the cell through this resistive heater. We will then measure the Newton's law of cooling curve and calculate that constant. We let it come to equilibrium again, which is at the top of the curve. We then turn it off, and then we measure what that delta T is, and we know how much heat we put in, so we can calculate the thermodynamic parameters, and that's shown on the next slide. This is more recent data. This one doesn't appear in the chart which I just showed you, but it's a typical calculation. You put energy input into a resistive heater. That's quite easy to calculate, the current times the voltage. You then calculate this Newton's law of cooling constant. In this case would be the 0.35 watts divided by the delta T, which we saw on the last slide, which will tell you how fast you're losing the energy to the surrounding bath, or when you multiply that times the temperature, you will get the total amount of wattage going out. So the heat output from the cell then is just the temperature difference. Our temperature of bath was 30 degrees, so there was a 6.86 degree excess heat inside over the surrounding bath. You multiply that times the Newton's law of cooling constant to get your heat output from the cell, the joule heat input. Again, Professor Bard explained how these numbers were obtained. You then obtain an excess heat then, in this particular case, of 0.47 watts. The next slide shows a comparison. We talk about break-even calculations. This is the point at which you generate as much heat as you are putting in. And this may be calculated by a number of different methods, depending on how you choose your electrochemical reaction and on what basis you make it. And these percentages then simply show what you can expect for the various reactions that are defined at the bottom. Most importantly here is that you can get extremely high. You can imagine reactions where you can get extremely high rates of excess heating. If you consider the reaction, if you were able to take the deuterium gas that you were forming in excess at the electrode and reconvert it into D2O, that's a very easy reaction to do, and if you could do that, then you can reach extremely high excess heating rates according to these calculations. You would do that similar, or with a cell that's similar to the one on the next slide, and that is simply to collect the gas over the cathode and pump it back around into a fuel cell type anode. Then the voltage required, the voltage input to the cell, very reasonably could be expected to be on the order of 0.5 volt instead of the 4.5 or 5 volts that we use right now. So you could expect to get much. So we get rid of the oxygenation reaction by substituting it with the reconversion of deuterium gas back to D2O. Okay, now on the next slide is just a breakdown of confinement parameters. The important parameter in thermal fusion, of course, is this concept of a confinement parameter. To reach ignition, you have to be something over 10 to the 14th in this Lawson or confinement parameter, which is simply a product of the particle density that you have. Professor Furth mentioned this earlier in the first lecture today, times the time at which these things are confined. Our equivalent diagram is shown on the last slide, and that is, we have the next slide, please. And that is something like this. We find that a confinement parameter, instead of being on the order 10 to the 13th, 10 to the 14th, is 10 to the 36th. So we make up in temperature here by a huge increase in this confinement parameter. We know the lifetime of the hydrogen in the lattice. We know approximately what our particle density is, and we can make a diagram like this. So the line across the center is the experiments for 64 milliamps per square centimeter experiments, and these are various rod sizes. We find that we have not reached break even based on this oxygen reaction. We find that these cells over here, or these rods over here, certainly have. The ones with the open circles are experiments under investigation right now. And we also anticipate that, and this again is absolute for the deuterium-deuterium reaction. We've had one ignition some time ago, so we can make an estimate as to where that region is, and that gave us a hint as to how to draw the break-even line here. And we also anticipate that if these reactions are done with deuterium and tritium, those being approximately 1,000 times faster, then almost all electrochemical situations may lead to at least the break-even region. Okay, in closing then, I'd like to have the last two overheads. First of all, I'd like to acknowledge my colleague, partner in this research, and that's Martin Fleischman, and a graduate student who did most of the work, Marvin Hawkins, Jerry Smith, who is now at Department of Energy, for his constant encouragement over the last few years and his knowledge of this project, Bob Hoffman and James Brophy from the University of Utah, and Ron Bullo and David Williams from Harwell Atomic Energy Establishment in England. And the final slide is acknowledgement of our support. Unfortunately, we had very little over the first few years, but we have indeed received more now from University of Utah, University of Southampton. Johnson Matthey lent us the rods, the palladium metal. Fortunately, we didn't burn up Martin's metal, which made him happy. And finally, I would like to acknowledge the Office of Naval Research, Bob Nowak, for now funding this work. Thank you very much.